Okay, so we are going to look at limits, and the part for limits where we focus our attention on is the use of L'Hopital's rule as well as the squeeze theorem. So what we really want to understand is how and when do we use L'Hopital's rule, and how and when do we use the squeeze theorem, because sometimes some questions on limits they can be a bit tedious. There are times when you are able to apply L'Hopital's rule, and there are some where you are unable to apply L'Hopital's rule or direct substitution, but rather use squeeze theorem. Okay, so to begin with L'Hopital's rule, um, what we need to understand is that for L'Hopital's rule, this is used when you try direct substitution, such that if you use direct substitution, it yields an indeterminate form. Like the answer that you get is indeterminate form, such as 0 divided by 0, or perhaps let me just indicate it as n divided by 0, such that n can be any integer. They're either negative or positive, as you're going to get undefined there. Or we say positive or negative infinity divided by positive or negative infinity. So if you get something that is in this form, it's simply said to be in indeterminate form. Okay, we say indeterminate form. Uh, Indeterminate. That's an indeterminate form. Okay, so that's when we use the L'Hopital's rule. So here, what do we do when we have something of this instance? It's more like let's say you have you say a limit as x approaches, let me say 0 let me try to use this example, the example that you're going to use. Actually, let's say we have a inverse of sine inverse of x divided by um, e to the power x minus 1. Here, if you use direct substitution, what you're going to get is 0 divided by 0, and that's what we are trying to avoid in this case. Okay, that's what we are trying to avoid, and of course we'll try to find a better way of expressing this one than it is appearing right now. Okay, and what it is here is that for us to be able to use L'Hopital's rule, okay, we need to understand that if, okay, if we say if the limit uh, of a function f of x, okay, as x approaches let me say a is equals to 0, okay, and the limit, let's say this is a different function now, as x approaches a of a function, let me say not we already used f of x, let me use h of x is also equals to 0, or so these are, we are trying to express a situation where we have an indeterminate form. So, or let's say we have a limit as x approaches a of f of x being equals to, we said, positive or negative infinity divided by positive or negative infinity. So in this case, what we need to understand is that for us to be able to find that function, I mean for us to be able to find the limit of that function as x approaches some number, okay, as x approaches some number, and what we need to understand about limits is that we are not really reaching at that number. For example, if x is approaching a 2, you are not reaching at 2. It's either you are approaching 2 from the right hand side or from the left hand side. It's like you have a 2 here, okay, so you're approaching 2 from this side and from that side. You're not reaching at 2 from this side. Maybe you can say it's 1.9. From this side it's what, 2.1, but 2 is just on the middle here. You're not really reaching at 2, but you're approaching 2 from either sides. Okay, and we understand that better when we start talking about the squeeze theorem. Okay, so here we can say if the function is giving us, if direct substitution is giving us an determinant form, what we need to do is that the limit, we get that limit of a function where x approaches some number, let me say a, of let's say you have a function that is in this form, f of x divided by g of x or h of x. Okay, to be able to um, to be able to work this out, we need to find the derivative of both functions. Okay, the f prime of x there, as well as what, g prime of x. If we still get an indeterminate form, go ahead and find the second derivative, f prime prime of x, then also find the second derivative of what, of g of x. If it still fails, you just keep on going and going and going. This is what L'Hopital's rule is all about. Okay, we differentiate the function that we have, and this is applicable most when you're talking about rational functions. Okay, so let's do let's go through a question. We see what you're going to get here. So let's say we have the function. We say we are given, we need to find the limit as x approaches 0 of the function uh, sine inverse of x divided by divide by e to the x minus 1. So at this stage, I might, maybe someone might not really know what you're going to get if you replace with 0 there. Okay, but when you look at it from on the denominator, if you say e to the power 0 there minus 1, any number raised to the power 0 is a 1, and we know that e is just a constant. So 1, we're going to have a 1 here minus 1, which is what, 0, and that's going to be undefined, and that's what you're trying to avoid. So what we do here is that we need to differentiate both sides, I mean the numerator and the denominator of what we have there. So we're going to say the limit as x approaches 0, then we need to differentiate sine inverse of x, or the arc sine. So here we need to be familiar with how we differentiate inverse trigonometric functions. Okay, so in this case, what you're going to get, remember to say, if you are looking for, if you have dx of uh, sine inverse of u, okay, this is going to be in the form u prime divided by root of 1 minus u squared. Okay, that's what you're going to have right there. So now, in this case, my u is x. Okay, my u is x, so meaning the derivative of x is 1, then square root of 1 minus, here we have our x squared. So the derivative of the numerator is going to be 1 over uh, root 1 minus x squared divide by, so we also need to differentiate what we have on the denominator there. So we have to say this is a constant, it to be 0, and we're just going to remain with what, we're just going to remain with e to the x here. Okay, of which I think we can erase this, of which what we have here, this can be written as, we say limit, we don't leave the limit here, so this can be written as 1 over e to the x there. Okay, we are multiplying by 1 minus x squared, root of 1 minus x squared. So when we reach this stage, we know we try to observe to say, okay, if we try to do direct substitution here, what are we going to get? Are we going to get something that is indeterminate? So we give it a try. That's the only way to know. So here you find that if you say 1 divided by e to the 0 here, then root square root of 1 minus 0 squared. This is simply 1 over, this e to the 0 is 1, okay, multiplied by, so you are going to have a 0, root of 1 is still 1, so you're going to get what? You're going to get a 1. So meaning here we have already found that the limit, we can say therefore, the limit as x approaches 0 of sine inverse of x divided by e to the x minus 1 is equals to what? Is equals to 1, and that's our answer right there. Okay, and that's simply how you apply the that's simply how you apply L'Hopital's rule. It's just a matter of you being able to differentiate. And if you find that on this first derivative you are getting an indeterminate, you're getting an answer that is indeterminate, differentiate for the second time. And if you're still getting the same, keep on differentiating until it's in the form that that is desirable. Okay. So now let's talk about the squeeze theorem. Okay, so just a brief statement on what the squeeze theorem is all about is that if you have um, if you have an interval, okay, if you have an interval, let's say you have an interval from this point to that point, okay, so we have that interval there, okay. So we say, let's say you have an interval containing a point. Within this interval, you have a point. Let me say somewhere here you have a point A, okay, and let's say you have three functions within this interval. Within that interval there, you have three functions. Let's say you have f of x, you have h of x, then you also have g of x. All right, and let them be functions defined on that interval. So let me name this interval as what letter can I use? Okay, let me use b. Okay, I'll use uppercase b. Okay, so f of x, h of x, and g of x, they are functions they are functions within this within that interval, the interval b. Okay, and you find that within this interval b, within this interval b, you are going to have a value of x. Okay, it's to be maybe somewhere here, to be somewhere here, and it's the same thing that I was saying. Like if you have x approaching a certain point, let's say it's approaching 2, I repeat, you find that what you are saying is that you are getting closer and closer to 2, but you're not reaching 2 itself. Okay, you're not just, it's like as I illustrated earlier, it can be 1.9999. You're not really reaching at 2, and you don't have to say I'll round off. No, we are not dealing with rounding off here. And here you find that maybe it is 2 point, let me say 2.0000000, maybe 8 something, and this is greater than 2. We all know that. Okay, so it's like you are approaching 2 but not really reaching at 2 itself. You don't have to reach at 2. So it's like you have a point within that interval, which is a. Okay, then you have a value of x, and that value of x is not supposed to be at a itself. Okay, and what happens that if f of x, h of x, and g of x, they are within that interval b, and we are going to say, let's say we have something of this form. Let's say we have our f of x being less than or equal to h of x, which is also less than or equal to g of x. Okay, and again we can also say suppose suppose um, suppose the limit as x approaches this point. Okay, as x approaches that point a, the limit of f of x is equals to some letter l. Then even we also say suppose the limit as x approaches a of of the function g of x also approaches l. Then we can say even. Okay, that means that, in fact, that means that even the limit as x approaches a of h of x is also equals to what? Is also equals to l. And for me, how I really like understanding this is in this way. If this and this, they're approaching the same value, it basically means what's on the middle is also approaching the same value, because h of x is within g of x and f of x. And how you can understand this better is, let's try to look at this. Let's say I have this bar here. Okay, let's say I have this bar right here. Then let me divide this into three parts. Okay, then let me say at this point I put my f of x. At this point I put my f of x. Then at this point I put my h of x. At this point I put my g of x. Okay, so what happens here is that I want to I want to convince myself. I want to convince myself that I want to convince myself that this bar here is shaded in one color. Okay, we say it's shaded in one color like that. It's not really perfect, but and we can see it's one color. Okay, and I've divided it into three parts. Okay, we say we have divided it into three parts there. So now the thing is that if f of x is red, or whatever that color is, or and g of x as well is also what is also that color, I'll call it red for now. That means even this one, if the entire bar is red, and what you have this side is red, and what you have this side is red, and we know that the entire bar is red, meaning even what you have on the middle is also red. Okay, that's what the squeeze theorem is all about. And why do we have to understand all this? There are times when you have some functions. Let's say there are sometimes, of course, they are rational functions, but they can also be a multiple of two functions, such as maybe you have x multiplied by sine of x. That's an algebra, and that's a trig. Okay, sometimes maybe even you have divide by anything here. Okay, so you find that maybe the function that you have is failing to fall to the spell of you being able to use L'Hopital's rule. You're able to use squeeze theorem. That's what the squeeze theorem comes to do. Is that it gets the function that you have, try to make it you try to make it simple such that you're able to work it out. It's just that the function that is complicated is h of x. Then the function that you get that to be much simpler, it is f of x as well as g of x. Okay, they will not be exactly the same, but the result are going to be the same. They will not look the same, but the result are going to be they are going to be the same, because we have understood that both of them they approach what the three of them they approach L. Okay, so the complicated function is what you're going to have here, on the middle part. Then here you're going to have something that is simpler, that you're able to work with without much difficulty. Okay, so now let's try to use the example. Let's try to use this example. Let's say you have the limit as x approaches 0 of x sine 1 over x. Okay, so I want to try to find that limit. Okay, so if I place a 0 here, it won't work out. Even if we place a 0 there, it also won't work out. Okay, so what do we do? What do we do? So one thing I'd like to emphasize is that one of the key things for you to understand as you use squeeze theorem is that try to put boundaries for yourself. And for squeeze theorem, we use it mostly when you're talking about trig functions. Those that would be sine as well as cos. They have constant boundaries, because the boundaries for sine and cos is just -1 as well as what as well as +1. So I can indicate to say, okay, I have -1 less than or equal to, here I'm going to have something less than or equal to 1. Okay, so I want to try to find out what those functions are that are going to be here as well as here, because those are the ones that are going to be much simpler compared to what I have here. So what happens here is that I'm going to write my sine 1, the angle is 1 over x. Okay, so the thing is that I've written what I have here. Okay, and I have that boundary and I have that boundary there. So like someone might say, okay, the angle here is not, remember to say sometimes you have sine theta or maybe sine x. We don't really care what is there. Regardless of what you have going to have there as the angle, the boundary will still remain the same. So I don't really care in terms of what we have as the angle. So in this case, what else can we bring in? You observe that from the function itself, we also have an x. And what's the relationship between the sine, that trig function, and the x is a multiplication relationship. They are multiplying each other. So meaning even this side you're supposed to multiply by x, even this side by what? By x. Alright, so that means you have what? Minus x less than or equal to x sine 1 over x less than or equal to x there. So you find that the function that I have here and the function that I have here is very much simpler for me to work with compared to what I have right here. So you find that you say the limit as x approaches 0 of minus x is equals to something, and this is the same as the limit as x approaches 0 of positive x is also equals to something. So here it's just a matter of replacing. You're going to find that when you place this will be equals to 0, okay, and this is also equals to b0. Therefore, okay, therefore we can say, therefore the limit as x approaches 0 of the function x sine 1 over x is also equals to what? Is also equals to 0. And there you got your answer. So squeeze theorem is very interesting actually. It gets a complicated function, then you make it much simpler for it to work with. Remember, like, try to check. I had x sine 1 over x, but I end up having minus x or positive x, which is very much which is even way basic for me to work with. So that's simply how you apply the squeeze theorem as well as the L'Hopital's theorem to deal with some limits that might be a bit difficult in terms of direct substitution, or as I said, it's not every function that is going to fall to the, yeah, to the magic of L'Hopital's rule or direct substitution. Sometimes you have to use squeeze theorem, and whenever you see trig functions, either it be sine or cos, just let it just ring a bell to say here I might be able to use squeeze theorem. And if you have it using other trig functions, it can be cosec, cot, tan, or anything. Try to use L'Hopital's rule. If it fails, perhaps maybe you can try to use identities. You put it in terms of sine and cos, sine and or cos, such that you're able to work with it properly. Because uh, here what you're focusing on again is the issue of boundaries. Okay, that's why -1 and +1, they are suitable as boundaries for what? For a sine function as well as a cos function. And that's simply how you go about answering those questions, or perhaps let's say L'Hopital's rule as well as squeeze theorem. Okay, so anything else beyond this, you can leave it in the comment section. And if you want to get in touch with us, you can WhatsApp us on this number, 0974004921. Okay, anytime we'll be very much available, and we'll be very happy to be of help. Okay, thank you very much for watching.